Hello everyone, we are from Group 2 and this is our presentation for the course MAA111 Algebra for Science Students. Our chosen topic is graph theory. These are the members in our group: Oong Xian Ming, which is me, my friends Wun Lim Zhe and Ernest Lim Shun. So, what is graph theory? Graph theory is a branch of mathematics that studies the properties and applications of graphs, with its primary goal being to understand the structure of these graphs and explore various problems related to connectivity, pathfinding, and network optimization. If we are able to analyze these relationships, we can gain insights into numerous real-world problems across a variety of fields. Now, let's learn more about the fundamentals. I will use the graph shown in the slide to explain. A vertex is a point in a graph. Here, we have 6 vertices: A, B, C, D, E, and F. An edge is a line connecting 2 vertices. In the graph, there are 8 edges. Degree is the number of edges connecting to that vertex. Hence, vertex E has degree 4. A path is a sequence of vertices where each adjacent pair is connected by an edge. An example of a path would be from A to B to C to F. Last but not least, a cycle is a path that starts and ends at the same vertex, like from A to E to D to A. We learned about the components of graphs in the previous slide. Here are some common types of graphs. A simple graph is a graph without multiple edges or loops, whereas a multigraph has multiple edges or loops. A directed graph has a direction associated with its edges, whereas an undirected graph does not. Edges in a weighted graph have value, such as displacement, while the edges in an unweighted graph do not. A cyclic graph is a graph with at least one cycle in it, and an acyclic graph lacks any cycles. A complete graph is a type of simple graph that maps each vertex to other distinct vertices. Vertices in a bipartite graph can be divided into 2 sets of vertices, where a vertex from one set only has edges connecting vertices from the other set. Finally, edges in a planar graph do not intersect when drawn on the same plane. So, why do we study graph theory? For starters, it acts as the foundation for mathematical structures by offering a framework and tools for solving a variety of problems. Objects and entities can be represented as vertices in a graph, with relationships between them modeled as edges. For instance, we can use directed graphs for mapping dependencies and weighted graphs to assign values to these relationships. The connection between all the vertices can also be viewed easily, which helps to speed up the study process. This enables us to derive efficient algorithms for solving real-world problems, like Dijkstra's algorithm for shortest route between 2 vertices. We will explore more about real-life applications of graph theory later, but for now, I'll pass the stage to my friend Wun Lim Zhe, who will dive deeper into the concepts of linear algebra related to graph theory.
Thank you, Ming. Good afternoon, everyone. I am Lim Zhe. Today, I will introduce all the linear algebra prerequisites which will then be used in our topic, which is the graph theory. Let us begin with matrix addition. Matrix addition is the operation to add 2 matrices to get a single matrix. For example, there are 2 matrices which are matrix A and B. The summation of matrix A and B involves adding corresponding element from the both matrices. Keep in mind that the matrix addition can only be occurred if both matrices have the same order. In other words, both matrices must have the same number of rows and number of columns. Let us continue with matrix subtraction. So, matrix subtraction is the operation to subtract 2 matrices to get a single matrix. For example, there are 2 matrices, matrix A and B. So, if you subtract matrix A with B, which means you are finding the difference between the corresponding element of A and B. Keep in mind that the matrix subtraction can only occur if both matrices have the same order. In other words, they need to have same number of rows and columns. For matrix multiplication, it combines two matrices to produce a single new matrix, which is known as the product matrix. In order to find each value in the product matrix, we need to take a row from the first matrix and a column from the second matrix. After that, we are going to multiply their corresponding value and add the result, which is known as the dot product. Keep in mind that the matrix multiplication can only occur if the number of columns in the first matrix match the number of rows in the second matrix. So for example, you are multiplying the matrix A, which has the order of 1 by 2, with the matrix B, which has the order of 2 by 1. Therefore, the order of the newly formed matrix will be 1 by 1, which has 1 row and 1 column. Adjacency matrix is a square matrix of size n by n, where n represents the number of vertices or number of nodes in the graph. Adjacency matrix can be used to represent the connections between the vertices of a graph. For unweighted graph, the matrix value are either 0 or 1. 0 representing there is no edge between the vertices, while 1 represents that the edge exists between the vertices. For weighted graph, the matrix values represent edge weights. If an edge exists between the two vertices, the corresponding entry represents the weight. Otherwise, it's either representing by the infinity symbol or INF. There are 4 types of graphs that can be represented using adjacency matrix. There are undirected and unweighted graph, undirected and weighted graph, directed and unweighted graph, and lastly, directed and weighted graph. Degree matrix is a square matrix. In other words, the number of rows and number of columns in the degree matrix are the same. Degree matrix is commonly used in graph theory. The matrix is diagonal, where each diagonal element represents the degree of a vertex. For unweighted graph, the degree of a vertex is the number of edges connected to the vertex, while for the weighted graph, it is the sum of the weights of the edge connected to the vertex. Let us talk about determinant. Determinant is a scalar value function of the entries for a square matrix. In other words, determinant can only be computed for the matrix where number of rows are same as the number of columns. For the matrix with order 1 by 1, the determinant refers to the element itself. For the 2 by 2 matrix, the determinant can be computed using the formula AD minus BC. And for the matrix with the order of n by n, the determinant can be calculated using a method called cofactor expansion. So here's how it works. First, we need to choose any row or column in the matrix. Then for each element in that row or column, we multiply it by a cofactor. And lastly, we add up these products to get the determinant of the matrix. Lastly, let us discuss about the eigenvalues and eigenvector. Eigenvalues are a special set of scalars associated with a linear system of equations. Let A represents a n by n matrix. If there's a vector x, which is an element of n-dimensional Euclidean space, where x is a non-zero vector, it can be represented by the equation ax equal to lambda x, where A is a matrix which represents a linear transformation, x is a non-zero vector which can be known as eigenvector, and lambda refer to the eigenvalue. Next, let us welcome Ernest, which will be presenting the real-life example of our topic, which is graph theory.
Now I will present about real-life or practical examples of graph theory, which are airline scheduling, city traffic analysis, community detection in social network, and Google PageRank algorithm. Now I will talk about airline scheduling using graph theory. Consider the following diagram which shows 6 cities and sum of flights between them. We can see that apart from Canberra, each city has at least 2 flights leaving from it. In mathematical terms, each of the cities is called a node or vertex, and the links between them are arch or edge. The number of arch leaving a node is called the degree of the node. Another way of representing this information is called an adjacency matrix. This lists the number of ways a node can be reached from any other node. Metric n represents number of one-step linked from one point to another point. For example, you can see from Perth to Brisbane it using only one step, and the matrix representation show only one possible way from Perth to Brisbane. From Perth to go back to itself by using one step, it is impossible, so the matrix representation shows 0. When you square the adjacency matrix, the resulting matrix provides the count of two-step path between cities. It tells how many distinct ways you can travel from one city to another city, exactly two steps. Example, the element at row P and column P indicates how many ways you can leave Perth, travel to another city, and return to Perth in two steps. You can see the diagram from Perth to Devon and from Devon go back to Perth. It only requires two steps, and it's similar for Perth and Brisbane and for Perth and Melbourne. Therefore, for flight planning, the airlines can check if a passenger can reach a city with exactly n layovers by adjacency matrix n power of n. It also for network robustness, if an airport closes temporarily, matrix n power of n helps find alternative n-step connections. For route expansion, the airlines can analyze potential cities to add direct flight to improve n-step connectivity. Let us move on city traffic analysis. The determinant of the Laplacian matrix, degree matrix minus adjacency matrix of a traffic system graph help calculate the number of unique spanning tree, which measures possible ways to fully connect all intersections. For a city graph, like shown in the slide, and then the determinant of this metric reveals connectivity properties. If determinant L not equal to 0, the network is connected. If determinant L equal to 0, some areas are isolated. Next, I will explain about community detection in social network. Consider a small social network with 6 users represented as a graph with the following adjacency matrix A. Interpretation: user 1, 2, and 3 are connected, forming one group. Users 4, 5, and 6 are connected, forming another group. No connections exist between these two clusters. The degree matrix D is a diagonal matrix where each diagonal entry represents the number of connections or degree for each node. To calculate the Laplacian matrix, we can use diagonal matrix minus adjacency matrix. Computing the eigenvalue of L, we can get lambda equal to 0, 0, 2, 2, 3, 3. The smallest eigenvalue, always 0, represents the trivial solution. The second smallest eigenvalue is 0, which suggests the graph is disconnected and show two separate communities. Social media like Instagram or Facebook can detect groups of friends who interact frequently and suggest group recommendations. It also identifies isolated communities to personalize content. The last example is Google PageRank algorithm. The eigenvector of the transition probability matrix helps rank the web page based on their importance and connectivity to other pages. Based on the diagram, we can see that from page 1 to page 1, it shows 0 possibility, and from page 1 go to page 2, 3, and 4, it shows 1 over 3 possibility. In Google's PageRank algorithm, the importance of a page is determined by the probability of arriving at that page from other linked page. Higher probabilities indicate a greater likelihood of users reaching that page, which in turn contribute to its importance in the ranking system. That's all our presentation. Thank you.